Okay, today we'll study section 4.3, the fundamental theorem of calculus. Recall that in previous lectures we discussed antiderivatives of functions. If you have some function f of x, you want to find capital F of x such that its derivative gives you your initial function. And such function is called antiderivative of f. And also last time we gave the definition of an area under a curve. So suppose you have some curve y equals f of x, and you are interested in an area between, say, A and B. And the definition was by the approximation of our area by rectangles, and this area is given by the definite integral of f of x from A to B. So this integral gives you area under the curve f of x between x equals A and x equals B. And in this lecture, we will connect these two concepts, and that will lead us to the fundamental theorem of calculus. So let's fix some number capital B. And consider the area under the curve bounded by vertical line x equals b, and on the right by a vertical line through x, where x is allowed to vary. So it's this shaded area. And as long as b is fixed, every value of x determines a unique value for the area. Thus, the area is a function of the variable x, and we will denote it by a of x. Let me draw another picture, and let x take in a small increment delta x. So now we have x plus delta x. And thus, our function a of x changed by an amount delta a. This is my delta a. So x to x plus delta x gives me a from a to a plus delta a. And let me introduce few points. So this point I will call t. This point I will call u. This point I will call p. This point I will call q. And also I will consider perpendicular to the line uq, and the intersection with that I will call s. And the same story from point q perpendicular to the line tp, the intersection point I will call r. And from the picture, we see that our area delta A is the area of PQUT, which is in general not a rectangle. But we can say that it's wedged between two rectangles. One is PSUT, so area of PSUT is less than area of PQUT, which is our delta A, but delta A is less than area of RQUT. And notice that PSUT as well as RQUT is a rectangle. And thus we can easily calculate their areas, because the area of a rectangle is just the product of base, and in case of PSUT it is just delta x, as we can see from the picture, while the height of this rectangle is the same as value of my function at point x. And so that gives me that the area of the rectangle PSUT is equal to base, which is delta x, times height, which is f of x. And it is less than delta A, which is less than area of RQT, which is also rectangle. So its base is the same delta x, but its height now is UQ, which is the same as value at point x plus delta x. And so I should put here f of x plus delta x. And so we have this inequality, and let's divide it by delta x. From the picture, delta x is positive, so it doesn't change the direction of inequality. And I get that f of x is less than delta a over delta x, and which is less than f of x plus delta x. And now let's recall the squeeze theorem, which says that if you have inequality of three functions, say f of x less than g of x less than h of x, and suppose the limit of f of x and h of x exists when x goes to a, then the limit of g of x also exists and is between those two limits. So in other words, inequality holds after you pass to the limit. And let's apply this squeeze theorem in our case when you have this inequality of three functions. And let's consider the limit when delta x goes to 0. So what we'll have? We'll have that limit when delta x goes to 0 of f of x is less or equal than limit of delta a divided by delta x when delta x goes to 0, and is less than limit f of x plus delta x when delta x goes to 0. And suppose our function is continuous. Then, by definition of the continuity, limit f of x plus delta x when delta x goes to 0 is equal to f of x. So on the right, we have just f of x, while on the left, we have limit f of x when delta x goes to 0, but f of x doesn't depend on delta x, so it's also just f of x. And we got that f of x less or equal than limit delta a over delta x, and which is less than f of x. And of course, from here, we can conclude that limit delta a over delta x when delta x goes to 0 is equal to f of x. But this limit delta a over delta x is nothing else but the derivative of a with respect to x. So we get dA over dx, or a prime of x is equal to f of x. In other words, a of x is an antiderivative of f. And so what we have? We have that our A of x, which is area under f of x between capital B and x, by the definition is equal to integral from capital B to x f of x dx. But on the other hand, if we denote f of x some antiderivative of f, we get that this a of this integral is equal to capital F of x plus c, because of the red box, because a of x is an antiderivative of f of x, and all antiderivatives of one function differs by some constant. And so we get this important formula, which is almost fundamental theorem of calculus. And the last step is to find the area under the curve between two specific lines, x equals a and x equals b. So what do we have? We have the following picture. So somewhere I have my point A and my point small b. And we are interested in this area, which is in fact difference of two areas. One is area between capital B and small b, so this one. And another one is the area between capital B and A, this one. So area between A and B is equal to area between capital B and small b minus area between capital B and A. But by the definition, this area is just integral from A to B f of x dx, while this second area is integral from capital B to B f of x dx, and the last one is integral from B to A f of x dx. But we just calculated that integral from capital B to some point x is just the value of our antiderivative at that point. So what I am saying that this integral is the same as f at point B plus some constant, while this integral is f at point A plus some constant. But the constant is the same, and so I get that integral from A to B f of x dx is the difference of two values of antiderivative. Antiderivative at point B minus antiderivative at point A. And constant c was cancelled. And so this result is known as the fundamental theorem of calculus. So the statement is the following. If your function f is continuous on interval ab, then definite integral from a to b f of x dx can be calculated in the following way. So it's f of x substituted from a to b, which is just the definition of the difference of value capital F at point B minus capital F at point A, where capital F is such that f prime is equal to f on the interval AB. So in other words, capital F is an antiderivative of f on that interval. So the fundamental theorem enables us to find areas under a curve by antidifferentiation. In other words, if you know the antiderivative, then you can calculate the definite integral, which represents the area under the curve. From now on, the process of finding an antiderivative will be called integration. So integrate means to find the antiderivative. And numbers a and b are called limits of integration. So let's do some examples. Let's start with this one. Integral from 0 to 3 x squared dx. So we know the antiderivative of x squared, which is x cubed over 3, one of them. And so I can evaluate this integral by substitution from 0 to 3 to the function x cubed over 3. And this is the value of that function at point 3, which is 3 to the power 3 over 3, minus value at 0, which is 0 over 3. And so I get 27 over 3, which is just 9. The same answer we got last time when we calculated this example using the definition of the integral, but it took us much more time to find this area, while here it's just one line. So the new procedure is somewhat shorter. And let's do another one. So suppose you have curve y equals 1 over x squared, and you're interested in the area between the lines x equals 1 and x equals 3. So in other words, you're interested in the integral from 1 to 3, 1 over x squared dx. We have the following picture, and we are interested in this area. And also we discussed how to find the antiderivative for any power of n except -1, and the formula was the following, that the antiderivative of x to the power n is x to the power n plus 1 over n plus 1 plus some constant. And so x to the power -2 will correspond to x to the power -1 over -1, which is just -1 over x. And thus, my integral from 1 to 3 of 1 over x squared dx, which is the same as the integral from 1 to 3 x to the power -2 dx, will be substitution of this function from 1 to 3. And so it's the value at point 3, so it's -1 over 3 minus its value at point 1, which is -1 over 1. And so it gives me -1/3 plus 1, which is 2/3. And this is the final answer. In some problems, the limits are not given, and you need to find them, as we will see in the next example. Find the area of the region bounded by curve y equals 1 minus x squared and the x-axis. So I have function y minus x squared, and let's draw it. So I have something like this. And indeed, I see that there is a region bounded by curve y equals 1 minus x squared and x-axis, so this one. And in order to find this area, I need to find the limits. So in other words, I need to find this point and this point. In other words, I need to find intercepts, and so I need to solve the following equation. 1 minus x squared is equal to 0, and thus x is equal to plus minus 1. So this point is in fact minus 1, while this one is 1. And thus my area will be definite integral from minus 1 to 1, f of x, which is 1 minus x squared dx. And we also discussed how to find the antiderivative for any polynomial. And so antiderivative of 1 is just x plus some constant, while the antiderivative for x squared is x cubed over 3. And thus I can find the value of my integral by substitution to the function x minus x cubed over 3 from minus 1 to 1, which is just value at point 1. So it's 1 minus 1 cubed over 3 minus value at point minus 1. That gives me minus 1 minus 1 cubed over 3. And so first gives me 2 over 3, while second I have minus 1 plus 1/3, which is minus 2/3. And I have minus in front of that parenthesis, so the final answer is 2/3 plus 2/3, which is 4 over 3.